Everyone should have learned about Pythagorean Theorem, at least if you have taken a geometry class in middle school. Everyone should also have heard about Einstein's equation E equals mc squared. But few of us have thought about any connection between the two. After all, why should there be any such a connection to begin with, given that the two seem to be totally unrelated to each other? Well, there have been some rumors lately circling in several social media groups about a proof of Pythagorean theorem based on the equation E equals mc squared. And the proof is supposed to be due to Einstein himself. Never heard of this? Let's find out what is going on here. Let's remind us what the statement of Pythagorean theorem is. Let ABC be the sides of a right triangle, where C is the hypotenuse. Then we have a squared plus b squared is equal to c squared. Euclid was the first person to provide a rigorous proof of this. After that, there have been numerous proofs for the Pythagorean theorem. In fact, there was a book that contains 367 proofs for this theorem. But here, let's see how this claim works. Okay, first, let's let E denote the area of a triangle ABC, and then simply apply Einstein's equation. We have E equals mc squared, where C is right here. Then we draw the height CD. This will divide our triangle into two smaller triangles, and we apply the same idea to each of the smaller triangles. And then we have EA equals MA squared by looking at the triangle on the left, where EA is the area of the triangle on the left, and A is the hypotenuse right here. And then similarly, we have EB is equal to MB squared by looking at the triangle on the right. Okay? Now, the triangle areas add up, so EA plus EB should be equal to the area of the total of the big triangle, which is E. All right, that is the same as to say MA squared plus MB squared is equal to MC squared. And once you cancel out M, then we have the result. Okay, sounds like a very simple proof, but certainly this proof makes no sense. In Einstein's equation, E stands for energy. It has nothing to do with the area of a triangle here. M is the total mass, and C is the speed of the light, and it has nothing to do with the side of a triangle here. So this proof is totally wrong, okay? That's wrong. It turns out there is a valid proof that does use an equation that looks like a E equals mc squared, and the proof was due to Einstein himself. Let's see how that proof works. First, we're going to start with the same picture as before. The original triangle plus the height that we added. Now, notice that these three triangles are all similar to each other. This is a well-established fact and has been used in some of the well-known proofs in Pythagorean theorem. But let's quickly show you why, for example, the bigger triangle ABC is similar to triangle CBD, the one on the left. Well, both are right triangles. The smaller triangle is a right triangle because we have a height here, so you have a 90-degree angle here, and the original triangle has a 90-degree here angle here. And then they both share angle at vertex B here, and therefore they have two pairs of angles that are equal to each other, and therefore the two triangles are similar to each other. Similarly, you can show the third triangle ACD is similar to the original triangle as well. So all three are similar to each other. Once you have that, then here is the key observation. There must be a constant denoted by M such that EA equals to MA squared, where EA is the area of the triangle on the left, and A is the hypotenuse here. And EB is equal to MB squared, where EB is the area of the triangle on the right, and then EC equals to MC squared, where EC is the area of the big triangle ABC. Well, this is a fact that works for any shapes, two-dimensional shapes that are similar to each other. So let's actually show you why this is true in the case of triangles. Let me actually give you a quick proof here. I mean, the basic idea is that if they are similar to each other, then the area really goes proportionally as the square of its side. So therefore, there has to be a constant m here. But let's look at the two triangles, delta and delta prime, that are similar to each other, and C and the C prime are two corresponding sides here. First, we're going to draw the height, h and h prime. So because they are similar to each other, let's assume that lambda is a stretching factor. In other words, C prime is lambda times C. And then likewise, because they are similar to each other, h prime must be equal to lambda h. They must be stretched by the same factor. And now if you look at the area is 1/2 base times height, so 1/2 C times h. And that will imply that E prime is lambda square times E, because once you plug in 1/2 C prime h prime here, you get a lambda square from here. Okay, so then therefore E prime over C prime square should be the same as E over C square, because you just substitute these things over here, then you see lambda square on the top and the lambda square on the bottom, they cancel out. So that shows they are equal to each other, and denote that ratio by m. And then we will have E equals mc square and E prime equals mc prime square. And that proves these equations. Okay. But once you have these equations, then the proof is really the same as before. Simply notice that the area add up. So EA plus EB is equal to EC. And then that is the same as to say MA square plus MB square equals MC square. And if you cancel out M, you get the result. This proof first appeared in this book by Manfred Schroeder, published in 1991. In the book, Schroeder told a story of the little Albert Einstein at age 11, who was learning some geometry with his uncle Jack Einstein. Now, Albert was not happy with the proof of Pythagorean Theorem in the book, so he came up with his own. The proof is really neat. The basic observation is that the area is proportional to the square of hypotenuse, but area add up, and therefore so do the square of the hypotenuse. That is exactly the statement of the theorem. So the proof really catches the essence of the situation. It goes into the heart of the problem right away. It is really elegant. By the way, the letter E here came from German word Ebene. It means level and region. So it's a natural choice for Einstein to use that letter here. Now, what about the fake proof that I showed you earlier? Where did that come from? Well, with the internet, a few versions of Einstein's proof were posted on the web. Sometimes people like to write fake proofs just to see if they can fool someone. I mean, doesn't it look like an April Fool joke? So, in 2005, Professor Xuejun Guo, who happened to be my undergraduate schoolmate from University of Science and Technology of China, he posted such a fake proof then. Magically, it did fool someone, who then copied this fake proof in a textbook, which then got published. Unbelievable. This is unbelievable. I won't release the name of the publisher, but it certainly was a terrible, terrible mistake. Not only because of plagiarism, but also such a lack of responsibility, especially with textbook. Now that we have finished explaining Einstein's proof, I would like to make two remarks. First, the main idea in Einstein's proof is an equation that looks like E equals mc squared. Of course, this is different from his equation in general relativity. Here, we are talking about similar like triangles, and E stands for the area and C is its size. I want to say that this equation really works for any two-dimensional shapes that are similar to each other. To give you an example, so all squares are similar to each other, and certainly we have the well-known equation, area of a square is equal to a squared, where a is its size. So this is the equation of this type where m equals to 1. For another example, all circles are similar to each other, and we have this well-known equation, area of a circle is pi r squared. So here, if you let radius to replace this c here, so we have an equation of this type where m equals to pi. For another example, if you look at all regular pentagons, as long as they're regular, all those regular pentagons are similar to each other. So there should be an equation that says a, the area of a pentagon is ma squared, where a stands for the one of its sides. I'm going to leave it to you to figure out what m should be. It is a good geometry exercise. So in general, if you have two-dimensional shapes that are similar to each other, then you have a constant m corresponding to that shape. So one can ask this general question, what is the best value of m? What shape will give you the best value? So let me actually post the following. So here is the how you phrase this question. What is the best shape that will maximize a over d squared, where a stands for area and d stands for diameter? So here we're talking about two-dimensional shapes. Every two-dimensional shape should have an area, and it should also have a diameter. It may not have an edge like a square, because like a circle doesn't have an edge. It may not have a radius. Some other shapes does not have, like a square doesn't have a radius, but you can always talk about a diameter. Diameter is simply defined to be the maximum distance of two of its points. Like for example, for pentagon, it will be like the distance between those 2 points. If you can guess what the best shape should be, you should feel good about that. It is actually quite a challenge to actually prove that is indeed the best shape. So don't worry too much about actually prove that. Let me move to my second remark. Here is a picture that appears in some of the standard proof for Pythagorean theorem. Basically, you start with a right triangle and then draw 3 squares along its sides. Pythagorean theorem, a squared plus b squared equals to c squared, really just says the area here is plus the area here is equal to the area of the third square, simply because a squared is exactly equal to area of a square. So we have an equation of this type. Area EA plus area EB is area EC. Now, if you look at Einstein's this equation here, if you have any similar two-dimensional shapes here, then the area is proportional to the square of its sides. So that means you can attach those 3 sides by other shapes that are similar to each other. You should have the same result. So for example, you can attach regular pentagons here. All regular pentagons are similar to each other. Therefore, we have area is m times the c squared. So because a squared plus b squared equals c squared, that really implies the area here plus the area here is equal to the area here for pentagons, regular pentagons. You can attach other shapes as long as they are similar to each other. Here is another shape that is semicircles. So basically you just start with a right triangle and then attach semicircles here, and then so you should have the area of those two should add up to the area here. Before I end, I would like to share with you a video that verifies Pythagorean theorem through an experiment. This video was created by Charles Hartstein.